So as we go on to section 5 of chapter 6, we're going to look at some word problems using rational equations. And one of the most common kind are those involving work. So again, when we have word problems, there's lots of reading. Again, I would look at the textbook, pause it, read it over. I will give sort of a summary of what's there. So we have 2 volunteers in a community garden. Brian can mulch the garden alone in 8 hours. Reggie can mulch the garden alone in 10 hours. How long will it take the 2 of them working together to mulch the garden? Now, as I've mentioned many times, keep in mind I have some additional exercises where I do a lot of this. And again, work problems are a major kind. And here's how I would do it. And there's a pattern that you can follow. Now, what is Brian's rate of work per hour? Well, he can get 1/8 of the job done in 1 hour. So his rate of work is 1 out of 8. And Reggie, and they're going to be working together, his rate of work is 1 out of 10. And the general form is, what will the rate of work be when they do it together? We don't know that. That's going to be 1 out of t. So this is the equation I use. The book varies it a little bit, and they are actually equivalent equations. I like it this way. So in solving it, you're going to multiply each term to get rid of the fractions by the common denominator. And you can set it up this way if you like. 8 times 10 times t. So you're going to multiply each term by that, and that'll take care of getting rid of all the denominators and turn them all into a 1. So here the 8 cancels out, and I'm left with 10t. 8 cancels out, 10 times t times 1. Now here the 10 cancels out, so I'm left with 8t. And here the t cancels out, so I'm left with 80. So I add these together and get 18t equals 80. Divide both sides by 18. I get t equals whatever this will simplify to, and that will be hours. So if I take a 2 out of there, I get 40, and if I take a 2 out of there, I get 9. So t is 40/9, but that's a improper fraction. I want to make it into a mixed number. So 9 goes into there 4 times. 4 times 9 is 36, and there's a 4 left over. So they would take this many hours getting the job done. Okay, let's see what they say. They're just going over various techniques here. Okay. And again, different strokes. So they're using a little different technique than I am. And in fact, if this is to show you how my equation relates, 1 over t. If I multiply everything by t, this was like a 1 there originally. This becomes a t, this becomes a t, and this just becomes a 1. So the equation I showed you and this equation are equivalent. They've just multiplied it through by t. Okay? I like the way I've done mine. It works out very well. So there's the answer eventually. And that's ours. Okay, let's take a look at example 2. Jody, 9 hours longer than it does Manuel to install a wood floor. Working together, they can get the job done in 20 hours. So how long would it take each working alone? Well, we know that one person takes 9 hours longer. So the rate of one person, we don't know their rate, it's going to be 1 over, I'm going to use the letter T for time. That's that person's rate. The other person, that rate is going to be 1 over T plus 9 hours. And that will equal, getting the job done together is 20 hours. So there's the basic formula using the technique that we had used before. Now, they're doing the letter M. I like the letter T. There are different ways. So let's go on. Now notice they end up with a similar formula, that this is over here 1 over 20, then they multiply through by 20 and they get this formula. Comes out the same. And the common denominator will be M or T, and T plus this. You're multiplying every term by that. And when they finish, well, not quite finish, but get it, they get a quadratic equation. And we solve quadratic equations by factoring, and we get two answers because it's a quadratic equation. But since we're dealing with time, can we accept a negative time to get the job done? And the answer is no. So we reject this one. And M is 36 hours. And then M plus 9 is 45 hours. As we will see, I'm pretty sure they're going to say that. And again, they're saying that -5 has no value in time. So 36 hours by himself, and then 36 plus 9 is 45 hours. But working together, they get it done in 20. Okay, and there is your answer statement. So model for working time. Again, they're using, this is the equation that I'm using. This is the one right here. Their rate plus the other rate is the 1 over the total time. Okay, we're now going on to motion problems, and we did a little bit of this in our other course. Here we're talking about distance equals rate times time, and we could also solve it for rate, and we can solve it for time. So part of what it is to realize what's going on. So I'll pause, set it up, and give you my best shot at it. So I've read it over and decided what is the same in this example. And what is the same is the time. So I'm going to the distance formula. Distance equals rate times time. And I'm going to solve it for t by dividing both sides by r. So I get time equals, and I don't like the way they've done it here, I like it this way, distance divided by rate. So we have then that time equals time, and one of the distances here is 80 kilometers, and one of the distances 50 kilometers. Now, we don't know the basic rate, so that's going to be r, but Paige, who travels this, has a rate that is 15 kilometers per hour faster. And this is what they do. So a longer distance, a faster rate. A shorter distance, a slower rate. So what we have here is actually a proportion that we'll be looking at a little later in the chapter. But what we can do whenever we have a proportion, we can cross multiply. I don't know if you've had this technique before. So our equation then for this problem will be 50 times r plus 15 equals 80 r as we cross multiply. So I went from my calculator and I distributed this, got this, subtracted 50r from both sides, got 30r equals this, divided both sides by 30, I get r equals 25. Now, what is this? Well, is that Paige has the 25 plus 15 will give you 40 k's per hour, and Sean is the one who does 25 k's per hour. Okay. And again, by reading this, and it wouldn't be practical for me to read everything for you, it gives you background, and using that 5-point strategy of how to get it done. And they even include making a little chart. So if you recall, this is what we had. We had it switched around, but that's fine. 50 over r, that is time. Distance divided by rate is time. Distance divided by rate is time. And they're using the other technique of multiplying everything by the lowest common denominators, but when we have a fraction like this, we can just cross multiply. It does the same. And there is your answer. Now this is the slower rate. We had to add the 15 to get the faster rate. Okay. And there is your answer statement. Going on to example 4. Now, again, I'm going to have to read this. I'm going to have to develop a strategy. And to keep the tape a little short, I will do that on my own time. But this is something you would have to do as well. Now, as we look at this, we have distance divided by rate. That's time. That's a portion of the time. And then the other portion, another distance, which happens to be the same, divided by the rate, is also equal to time. So we have going upstream, one of these actually going against the current, and then going with the current is the faster. So, but the total time is 5 hours. So 24 miles is the distance downstream. The speed of the boat in still water is 10, plus the speed of the current moves the boat faster. Now going upstream, again it's still 24 miles, but the speed of the boat is 10 miles in still water, minus now because it's going against the current, C, and the total time is 5 hours. So there's your basic equation, and you're going to multiply everything by, ran out of room over there, but it will be 10 plus C, 10 minus C. And we would FOIL that, multiply it by 5 over here, and then for this 24 we're going to cancel these out and multiply it by this, and this 24 we're going to cancel this out and multiply it by that, and then again there's a lot of work to be done on this, and since they have it all written out here, I'm assuming they made a little chart. Okay, there it is right there. This would be going upstream, you're going against the current, and it's 24 divided by this, downstream with the current. Okay, a lot of nice pictures here. And then they actually show you the work here. So let's pause for a moment and take a look at this. Okay, so there's our common denominators. We're going to do what I said. My wife gave me a little call, so I had to go to her aid. But here's our basic equation then. Multiplying each term by the common denominator, as we said. We then get this. Now I would transpose the negative to the other side, bring this to the other side, factor out the 5. Here I get the difference of perfect squares, factor that, equate each of them to 0, and I get that the current is either 2 miles an hour, or as they say in the twilight zone, the current is negative 2 miles per hour. So we're going to reject the negative. So the current is 2 miles per hour. And that is that one. Okay, we're now going on to proportions. So as we look at proportions, proportion basically is a ratio of two quantities, and that's a quotient, a fraction. So for example, 37% is a ratio of 37 to 100. That is 37 over 100. Now, when we have proportions that are set up as an equation, we're saying this proportion is equal to this proportion. And we have a name for the A and the D. The A and the D are called the extremes because it's the furthest out this way and furthest out this way. And then the C and the B are called the means because they're sort of in the center. And what we know, and I've mentioned this earlier, but now I guess this is where we're going to show you, you can actually multiply the extremes, A times D, and get AD, and multiply the means and get CB, or BC, and we say the product of the extremes equals the product of the means. That justifies our being able to cross multiply. Now, there's also applications to this in geometry where you have, and I think they're going to show us this, similar triangles. So here in similar triangles, you may recall the angles are the same and the sides are proportionate. So we can use this proportionality to set up missing sides. So let's take a look at it here. Now we're saying that in this similar triangle, this side here, 5, is to 8. 5 is to 8 as Z is to 10. Okay? Now there's other ways to set it up too. That was the way I chose. So we can cross multiply and we get 50 equals 8Z. Divide both sides by 8 and we get Z equals 25 fourths, which is what they have right here. 50 divided by 8, or they're giving it to us as a decimal fraction. Now 4 will go into there 6 times, and 1/4, which is 6.25. Okay. So here we're dealing with an architect and a blueprint. It's a scale drawing of a building. And I have to reduce this a little bit in size. There we go. So let's study this, and again you're going to have to read it, look at the diagram, and I have to do it too. So the key, and when we are setting up proportions, is we must have a follow-through in our proportion of what we're comparing. Here we're comparing inches to feet. So we have 2.5 inches there to 10 feet. Well, if we're going to extend this house or apartment 12 feet, how many inches would it be? So again, we would just cross multiply and get 10i equals, So 2.5 times 12 is 30. So now we divide both sides by 10, and we get this is 3. So over here, this will be 3 inches. And these two little marks here indicate inches as a shortcut, and a single one is feet for any of our foreign students that may not know what that means. Okay, let's go down, or next, I should say. And there's the work. Okay? And again, I would use cross multiplication much better than having to use the common denominator. All right, now in wildlife population, and here what they're going to do is tag, I believe, trout. They put a little tag on them. And let's read this over and come up with a strategy. Not sure I mentioned this before, but I have a background in biology. I was a biology teacher for many years and also had a sideline of environmental science and actually did something like this, but we were doing it with eels instead of trout. So again, you're going to have your ratio of tagged to total population. So you went out one day and you caught this many trout and tagged them. Did you tag the whole population? No. So this is the whole population. You tagged this many of them. Then you went out another day and you caught as your total population 915, and of those 24 were tagged. So this was the tag to the total population, tagged to the population again that you sampled. So to find then what would be your estimate of the total population, you're just going to cross multiply. And when you do that, and they have the work down here, they're using a little different technique. I like the cross multiplication. So this would be 24p. And I guess this number is whatever that is. It's a big number. You're going to divide by 24 here. I guess I should write that in. So when we multiply these, we get this big number. And then when we divide it both sides by 24, we get our population is estimated as this, which is what they get here. Okay? But again, tagged to total population. You took this many out, but you didn't know the total population. Then you took this many out, and this was a sample of your total population, and 24 were tagged. So there's your ratios. You cross multiply, and then you estimate your population as this. And by the way, this is a very common thing that we use in field ecology, where we're trying to figure out what our populations are. And again, many examples in your textbook, and I have that page or pages of additional examples in which I work out each of the equations for you. And for students with English as a second language, this could be rather difficult, but again, we're going to just do a few, and we're not going to try to pick out the hardest ones to do. And we kept this just under 30 minutes. Good.